Okay, so today we're going to go over section 1.4, chapter 1, section 4. There's a good amount of topics. It's going to be a heavy dose of algebra in this one, so you're going to see a lot of algebra. Really going to get into it here. So, like always, I'm going to start with a couple PowerPoint slide lecture, and then I'm going to go and do some example problems here after the fact. All right, so topics we're covering: all the properties of polynomials, polynomial regression using a calculator. We'll do a little bit of that, but not a ton. I'm going to focus more on the other concepts, properties of the rational functions, and then, of course, our applications of the polynomials and rational functions. So starting with a polynomial, this is the one that has a series of terms in a row, added or subtracted together. Okay, any kind of a function like that, we've been used to dealing with squares and some power threes, but it might be something like a power 5 function. Something like this. So you see the general way, just have a number of terms. There's 6 terms here. You normally want to write it with the highest power first, and then work your way down to the lowest powers. And of course, at the very end, and that's supposed to be a 4x right there, negative 4x. And your very end is your constant, your last term without any variable. So that's what this format is right here. It's not exactly always the most clear, but that's what they're going for. That's what they're saying is let's start with the highest power of n, what it's going to be, and that highest power, so you know, that's going to be your degree. This example I gave you as a polynomial of degree 5. And the degree is important because we're going to use that throughout this chapter and future chapters to determine our course of action. Whether that lead power is odd or even, there's different things we do. And of course, there's different ways the graphs look for each of these. Okay, so your domain of any kind of one of these polynomials is going to be all real numbers because it is just single powers of x. We're not talking about fractional powers. We're not talking about fractions yet. We're not talking about square roots, cube roots, any of that stuff that we kind of had in the first couple sections. It's just going to be a number of terms added up. So when that's the case, there's no restriction on x. It can be anything. That one I just erased, you could plug any x into any of those values there for x, and it's going to be fine. The range is going to vary. Now, if you have an odd degree problem, you'll see in a bit, the range is going to be all real numbers. Everything from negative infinity to infinity is going to be existing for y. When it's an even power, even degree, then it's going to be, they say it's a proper subset of reals. Essentially, it's going to be partially, kind of like those parabolas we did just in the last section where, the range was everything from the vertex on the way up or everything from the vertex on the way down. It's going to be kind of like that here when you have an even degree polynomial. And then a constant function, we'll deal with that a little bit. That's when the polynomial has a degree of 0. That's the thing like y equals 5, y equals 10, y equals negative 3. That has a degree of 0. Okay, a linear function, the highest power is 1, so it's a degree of 1. And a quadratic we dealt with has a degree of 2 because the highest power is 2. So we're going to focus on just the odd degree polynomial graphs for a second, just to see how the odds look. And remember, that means the highest power is 1, or the highest power is 3, or the highest power is 5, 7, etc. You can have even powers in these, but we're just talking about the degree, so that refers to the highest power. So when you have that, they cross the x-axis at least one time. And you'll start to see in a minute why that's true. But here's kind of an add to that. We said that the range is going to be all real numbers. So if you go all the way from negative infinity to infinity, at some point you've got to cross 0. You have to cross the x-axis. So you're going to have at least one x-intercept. And it may bounce up and down, so you may have multiple ones. All odd degree polynomials with a positive leading coefficient start negative and end positive. English, here's what this means. If you have something like y equals 7x fifth plus 8x fourth, and the other ones, I'm not going to write them yet. These other terms don't matter. The lower terms, we're just going to focus on this. So that means we have an odd polynomial, which is what we're talking about here. If this is a positive coefficient, your graph is going to do something where it starts down here at negative infinity, and who knows what happens in the middle, but it's going to end up here. It's the start and the finish that we care about. That's what happens whenever you have an odd degree and you have a positive leading term. Okay, that's the deal. That's what's going to happen there. So if you have a negative leading coefficient, I'll show you how that flips around, how that changes. If that first term, now remember, we're still talking about, this page is only about odd degree polynomials. But if you happen to have one where the first term is negative, and again, I'll kind of do an example here. And it doesn't matter the other terms. Okay, all the following terms, we don't care if they're positive or negative. We're just looking at this one. So here's an odd degree. Here's a negative to start. Okay, so when that happens, we're trying to figure out what's the case going to be. So remember, if it's odd and this first term, we're not worrying if the coefficient's odd or even. We don't care about that. We just care about the sign in front. When it's positive, your graph did that thing we just did a minute ago, where it starts down here and ends up in the top right. On a negative, it's the exact opposite. It starts up high, action happens in the middle, and it ends down low over here. So this is a positive leading coefficient. This is a negative leading coefficient. And we'll talk about what happens here in the middle. So don't worry, like, how did I get all that? I'm just kind of using that as a placeholder. But what's important is how these graphs finish and start. This is what happens on a positive odd polynomial. This is what happens on a negative odd polynomial. Okay, so that's what they're trying to demonstrate here with those two lines. Okay, so now they're going to talk about what happens when you have an even polynomial. Now remember, if you're ever unsure, start to think about the one even that you guys know, the quadratic, where you have a power of 2. You know, if I have something that looks like y equals 4x squared plus 3x minus 9, that's a parabola that's pointing up. If you have a negative, same thing, it's pointing down. Remember, we talked about that in the last lecture here. So use that idea here, and that's what we're going to talk about with these even degree polynomials. Okay, doesn't matter if it's a 2, 4, 6, 8, or 10 to start there. Some even polynomials never intersect with the x-axis. Okay, so it's possible that if this is my axis right here, see this parabola here, it never hits it. So you may not get an intercept at all, or you may get multiples, or you may get one. You know, there's just, it's not totally clear. So if you go back 2 slides, remember they said odd degree polynomials always hit the x-axis once. Here with the evens, you may not hit it at all. But in both cases, you may hit it multiple times. So even polynomials that start positive. So remember we talk about this front number right here? If this is a positive 4, it starts positive and ends positive when it has a positive leading coefficient. Starts positive way up here and it ends way up here. If it has a negative leading coefficient, it starts negative and ends negative. And this doesn't matter if you're dealing with a power of 4 or 6 or 8. Anytime you have an even degree, an even highest power, if it's a positive number in front, you're going to start high, and you may have a lot of action here, but it ends high. If it's negative and you have an even power, it's going to start low, something happens here, and it ends low. So that's the 2 scenarios you're going to get when you talk about these odds and you talk about these evens. Okay, so now they're going to do an example here. We're going to graph the function f of x equals x minus 2. How that thing looks. So it's an odd degree, and you may not realize it. This is just a linear a line like we've had in the last couple sections, and like you've had many times before in algebra. But it's going to fit the same narrative that I talked about earlier. It's an odd degree. The highest power of x you see here is a 1. This is an odd degree. So the property is it's going to hit the x-axis at least once, and it's because that first term is positive right here, it's going to start somewhere down. Oops, sorry. Let me bring that. It's going to start somewhere over here, and it's going to end up here. That's what happens when you have an odd positive. Positive first term, and it has an odd degree. So they graph it, and again, you know how to graph a line, but you see it sort of fits that thing we talked about. It doesn't have to be a high power. Any odd power, this is going to work. Okay, so now we're going to graph an odd degree polynomial function. It's x cubed. Now notice it's the same thing. It's a positive, so it's going to be starting down here, and it's going to end up here. Now, one way I like to look at it is, if you have an odd degree, the power, it starts and finishes at different spots. If you have an even degree, it's going to start and finish at the same, like both high or both low. This is an odd degree, it's positive, it's going to look like this, and you plug it in, this is what we get. Now notice in both these examples, we're talking about just plugging these into a graphing calculator, so you're not expected to just come up with these. This is just giving you examples of how it's going to look and how it fits. Okay, now we start getting to a higher power of 5. Same thing, it's a positive, so it's going to be on the left side, it's going to start in the negatives, and as you finish on the right side, it's going to end in the positives. And what I want you to see in all three of these cases, as that power starts increasing, that's when you start getting more action inside of the graph. So look at this graph, see how many turns you get. Lots of turns, lots of action inside there. Okay, so check that out for a second. Okay, so let's move on here. Now we start talking about even polynomials. Now remember, when I say even, I'm talking about the power, the highest power. The last three were even, highest powers were odds, odd degrees, so it had those properties. Here they're even, so remember the property is that it's going to start and finish either both on top or both on the bottom. Because that first term is a positive coefficient, a positive 1, it's going to start at the top and it's going to end at the top. And of course it's a parabola, this is how it looks. And also remember that one statement they said earlier where it may not even touch the x-axis. Here's an example of one that there's no x-intercept. That is a possibility. Now we get a power of 4. Same thing. Make sure you check all your powers. Make sure that is the highest power, which it is. So it's an even polynomial, even degree. First term is positive. So just like the last one, it's going to start up high and it's going to end up high. But because it's a higher power, we get more turns, more twists and turns here in this one. Okay, now we get power 6, and you see the same kind of things are happening here. Ending and the start and finish are important in graphs. Even though we focus more in the middle, you want to know where these graphs end and finish, as in these both end up high in infinities. Then you just have to fill in the blanks in the middle. And as you can see, the more terms, the more powers, the more action and turning you're going to get in the middle. Okay, so a couple things here. A couple things we'll go through here. Starts negative, ends positive. We talked about that. The ends of the odd degrees moved in opposite directions, and I said that as well. Remember, if it's an odd degree, it's either the two ends are either pointing in, they're always going to be pointing in opposite directions. Okay, cross the x-axis at least one time. That's a guarantee, maybe more. Even degrees, they start positive and end positive if they have a front number that's plus. Or I didn't say it. If it's negative, it's going to have them both starting and finishing at the bottom. And some even degrees will cross the axis, some did not. It's not a guarantee. And the last little statement about the graphs here, the ends of each even degree polynomial moved in the same direction. That's what I was saying, where when you have a power of 2, 4, 6, or 8 as your leading degree, your leading power, the graph either both sides point up or both sides point down. Just think of it. Even degree powers are like parabolas. There just sometimes is a lot more going on in the middle. Okay, some more observations. No graph cross the x-axis more than their degree. And that's an important case here. I didn't go back, but I'll pull up that last one that had a power of 6. Notice it hits the x-axis 4 times, 4 different times. You're never going to get it more than what you have there, more than the degree. Okay, so that degree 6 is the maximum number of times you'll hit the x-axis. You're going to hit it either that or less. So that's one way when you're solving these problems, they're going to ask you, give me all the zeros, tell me all the x-intercepts. If you see it's a power 2, you know there's either 0, 1, or 2 times you're going to hit the x-axis. If you see it's a power 3, you know it's going to hit at least 1 time. Maybe it hits twice. Maybe it hits a 3rd time, but it's not. That's your maximum. Whatever the degree is your power. Then the other one, I love this one. Changes in degree are limited to 1 less than the degree. So if I had a function like this, okay, something like that. it has a degree of 4 from that highest power. What that means is if you subtract 1 from it, n minus 1 equals 4 minus 1, jumping the gun here. This is the maximum changes in direction. I'm going to call it turns. Okay? It's just like if you're driving a car and you do a U-turn. Think of it more as U-turns. Maybe I wouldn't say U-turns is better. Maximum of 3 U-turns. So I'm going to go back one more time to that graph that had a power of 6 that we plugged into the calculator and we graphed it. Okay, right here. The degree is 6. That means you subtract 1 from that. That means you're going to get at most 5 changes in direction, turnarounds. So imagine I am traveling along this, and I'll try to use a different color here. So you see I'm coming down here. Here's my first turn. Here's my second turn. Here's my third turn. There's my fourth turn. There's my fifth turn. That's it. 5 turns. 5 U-turns. And that's always going to be 1 less. So you're never going to have a graph turning 8, 9, 10 times if the power is 6. It's always going to be exactly 1 less or even less than that. That's the maximum is going to be. In this case, I know that from looking at every graph. So when you have a parabola, you see a power of 2, at most, that thing's going to turn around 1 time. Okay, 1 less. If you have a power of 1, a line, think about it. A line has a degree of 1, so at most it's going to turn 0 times. And that's what a line does. It never turns once. So that's what we're talking about when we're making the turns. That's what we're dealing with in each of those cases. Okay, so go back to where we were. And polynomials are continuous functions. And that's an important one. When we say continuous, what that means is you can draw this with one motion of your pencil or your pen. You don't have to pick up your pencil. You don't have to jump. There's no holes. There's no gaps. There's no sharp turns, as in like 90-degree turns or points. It's a nice smooth graph that you can just draw, and that's what they mean by smooth. It's a nice constant graph that you have. Now, show you another one. This is a case of something that's not continuous. It's discontinuous. At 0, there's a big gap. There's a big jump right there. Okay, that's the graph right there. Not continuous because there's a big hop from one side to the other. Not continuous. It's continuous, but see how that's a corner? You can't really smoothly draw this. That's a smooth graph, but you have to like stop and turn. That's what they mean by it not being smooth. There's a sharp corner like a point, so that one's not going to be as smooth. And your last one, this is a case that's continuous and smooth. So now we talk about a rational function, and as you can see, they talk about rational functions. It looks like it's a function over another. In English, it's a fraction. It's where you have a polynomial on top of a polynomial, and any kind of a combination. And it's a whole different game here, but the domain is normally going to be all real numbers, and the exception is, as you know, you can't have anything on the bottom of a denominator of a fraction equal to 0. So if you take that bottom function, whatever it is, and you set it equal to 0, any of those x's are basically excluded from the domain. So you started out with all real numbers, but then you just take a couple back is how I generally approach this when you're dealing with the domain of a rational function. So there are quotients of polynomial functions. Like I said, it's dividing. We're division of these. And we've got a few here, so we've got to look at these. And you have a function that's x minus 3 and a function that's x minus 2. The rational function is going to be, and I'll add that because I don't have it here. The one we're looking at is x minus 3 over x minus 2. This is how you're normally going to see it when you get a problem. Okay, so I guess they write it right here, so you can see it without me writing that. But now we want to find what's the domain. So we want to write the rational function. There it is, this one right here. That is the function. And the domain, remember, you set everything on the bottom not equal to 0 or equal to 0. Just find the places where x will not work, and right there, that's your exception. So it's all real numbers except you cannot have 2. So your domain is going to be all real numbers other than x equals 2, the one thing that you cannot have. Okay, so we have a vertical asymptote. So if you remember asymptotes before, these are lines where your graph approaches it, but it never quite actually makes contact with it. It's like guidelines is how I like to call it. So a vertical asymptote, of course, means it's a line that's vertically going up and down. So if you look at it here, we have a vertical asymptote of x equals 2. That's this right here, x equals 2, that vertical line. This is the one place, if you remember too, we talked about x cannot be equal to 2. That was not in the domain. So your graph will have no point on the x equals 2. That's why you have that dotted line there. It shows you that you're going to get real close to it, but you're never going to quite get there. And it's the equivalent of like a hole on a graph, but in this case, when you have something on the bottom like that, it generally is going to represent a vertical asymptote. So this right here, remember, x minus 2 cannot equal 0, therefore x can't be 2. I immediately will go and draw this dotted line, which means it's not part of your graph, it's just your guideline of what a vertical asymptote is. Okay, so we'll get to the horizontal asymptotes in a little bit, but that's the one going, let me get rid of that, go back. This one right here is another asymptote where you can't just see it when you go on the graph. I'll show you some tricks later on how to get that, but that's also what's happening. For most rational functions, it's going to be these two regions where they're kind of like diagonal parabolas, and they're wrapped around these two asymptotes. Now I get a different function where it's also a rational function, just like this, and remember, first step, let's set that bottom equal to 0 to learn about our domain. Now these are like the problems we did the other day. Remember, it's like a parabola. Where is it? Sorry, equals 0. Let me go back. Not that. Factor this is what I meant to say. Sorry. And we learned that you can't have a 2. You can't have a negative 2. So our domain is all real numbers except these two. Hence the dotted lines, the two different asymptotes that we have here. Okay, so we use those. And those guides are actually very helpful because they help us draw the picture. Okay, now we start plugging in points, and again, this talk right here, this slide is just to learn about where these vertical asymptotes come in. But it breaks up your picture into 2, 3, 4 chunks, and then you graph separate graphs. And of course, as you can tell, these are not continuous like we talked about earlier with the regular polynomials. And then, of course, we have this last one. This comes up sometimes, but you have one of these where it's, and I don't know if I actually will say I like what it says here. I'm not going to go with that one, but right here, you cannot have x equals 0. So my domain is all real numbers except for 0. It technically is going to be an asymptote right here at x equals 0. I'm not sure why it said that, so just kind of ignore that for now. Apologies on that. But there is one vertical asymptote right here. What it doesn't have is it doesn't have a horizontal asymptote. It has one of these that we'll talk about called a slant asymptote. But again, these are guides. Right now, we're just worrying about how to get the verticals, how to get those, and then we start graphing around those. And as we're getting closer and closer to them, that's what happens as it goes further and further out. So horizontal asymptotes, this is the ones we're supposed to be doing now. These are the ones I said where it's right here, and it's not always easy to tell from the picture. You know, like looking at that picture, I can see that you can't, or sorry, from the equation, looking at it, I know that x cannot equal 2. Okay, so there's my vertical asymptote right here. But the horizontals you can't tell as easily. What a lot of this is going to be is as you start graphing this, and there's a couple tricks I can give you, but as you start graphing the picture, you're going to notice as your graph goes further and further out toward positive infinity here, you're going to see a pattern, and as you go toward negative infinity, you're going to see a pattern. And I'll say what I mean. Let's say we plug in x equals 10 way over here. When you plug that in, you get 10 minus 3 over 10 minus 2, and we get 7 over 5. Okay? So, did I do that right? I apologize. Okay, 7 over 8, I'm sorry. I'm doing my math wrong here. 7 over 8. Okay, so it's going to be a number that's close right there. Now, we can't plug in infinity, but what we can do is we can plug in really big numbers way out here. Why don't I plug in 100? And when I plug in 100, I get 97 over 98. And you see what's going on? This fraction is getting bigger and bigger, but it's not really growing that much, but it's growing enough, and it's still always going to be just under the number 1. If I plug in f of 1,000, I get 997 all over 998. Again, it's slowly rising, but it never hits this 1. That's how you kind of get an idea of what the asymptote is. It's just above this number. And it's the same thing if you went to the left. Let's plug in negative 100, and you get something like negative 103 over negative 102. And as you go further and further out, you're still above the number 1, but you never quite get there. And that's the way we figure out what the horizontal asymptote is. And in the beginning, I'll show you a trick later, but for now, just look at it as it's how you get the, you just go get some points to the far right and the far left. And like I said, instead of infinities, just plug in really big numbers. Now, the difference of horizontal asymptotes is a vertical asymptote, you can never touch it. A horizontal asymptote, technically you can cross over. What I mean is, we still will plug in big numbers, and you're going to see that this horizontal asymptote is going to be at, y equals 0. Because it gets closer and closer to 0, but never gets there. Same thing on this side. It is possible sometimes in the middle, though, your graph may. It didn't cross this time, but you may cross the horizontal asymptote. Not always the case, but the horizontal asymptote is not a banished number like the vertical asymptote. It's more of a guide as you go further out to the far right and the far left. That's what's happening when you talk about your horizontal asymptotes. Now, this last picture here, okay, this is what they meant to say in the last problem. There's no horizontal right here. They said no vertical in the last slide, so I apologize. That was just a misprint. They did have a vertical asymptote, but there's no horizontal on this graph. What it is, like I said, it's called a slant asymptote, where it's where your graph is going. And basically what happens is, as you get, you could figure out the same approach, but it may not be as obvious. Go plug in something like f of 100 and see what you get. What you're going to learn is, as you go further and further to the right, that number holds constant. This fraction gets smaller and smaller and smaller. Think of it, 1 over 100 is like almost 0. 1 over 1,000 is almost 0. This line right here is basically y equals x. That's the slant asymptote. Now, I don't want you to get wrapped up on that right now. We're just going to worry about the horizontal and verticals today. Mainly the verticals is what really is the priority. Once you start mastering that, then we'll go to the horizontals, and then we'll move on to the slant ones later. Okay, so this is important. The denominator of a rational function has degree n. Okay, so just the denominator. Look at the degree of only the bottom. That's going to tell you that you're going to have no more than that many vertical asymptotes. So go back again. Remember that first equation right there? The power, the degree of this bottom, the highest power is 1. That means at most you're going to have 1 vertical asymptote, and there it is. Here, the highest power is 2. So you may not, but at most you're going to have 2 vertical asymptotes, and that's what you get right there. So that's why these degrees are important, because these are all identifiers and traits that you can pick up right from the beginning just by looking at the picture. Okay, this one, different case, so we'll talk about that one later on. So, all right, go back here, I'm sorry. Second bullet there, numerator, then the rational function has no common zeros. If it has no common real zeros, then the top is going to be 0 and x is c. Vertical asymptote, it's kind of, there's a lot of wording in there. I'll kind of give this to you in English here. If there's no zeros, like you can't solve for 0, we don't really have any of those right here. I'll give a better example, excuse me, as we go there here. So ignore the 2 for a second here. Let me jump here. I don't want to give you too many theories at first. Let me actually get to some examples. So I'm going to run through these a little bit faster. But the horizontal asymptotes, again, normally it's going to be y equals 0. Okay, rational function with numerator degree less than the denominator is going to have a horizontal asymptote of 0. Again, the numerator degree. So I'm going to go back again. the degree of the top. If it's less than the degree of the bottom, then you know your horizontal asymptote is going to be right here at the x-axis, y equals 0. That's if the bottom degree is bigger. Okay, here it's the same, so it's going to be something else. Here it's bigger. This has a degree of 0 on top. This has a degree of 2. The bottom has a bigger degree. What that means is you're going to get a horizontal asymptote of y equals 0. That horizontal line right there. And this one, again, is a unique case, doesn't have one. So that's one of the shortcuts. So I'll come back to these because, like I said, I don't want to fill you too much with these. You can read these, you can come back to them, and we can look at them later on, but I want to get to some examples like this one. Find the vertical and horizontal asymptotes of the rational function. Okay, so first off, two polynomials, one on top of the other. So first off, factor the numerator and denominator to reveal common factors. So this is what they meant when they said common factors, and I'll show you that right there. I don't like calling that n of x. I like to just go ahead and factor the top right here and the bottom right there as well. Okay, so this is what the bottom is, and this is what you get. So when you reduce the top fraction, you'll notice that we have a common fraction, a common factor of x minus 1. That's how it reduces down to this. Okay, so first off, what this top means is, remember the denominator cannot have anything that equals 0. Before I canceled, I factored the denominator and I say, well, what values make it equal 0? What are my bad values? What are my values that are out of the domain? Can't have a negative 1 and a 1. So no matter what happens in this problem, we can't have those two numbers at all. They don't exist. Now, are they asymptotes or are they going to be something else? You'll see in a second. If one of these factors cancel out, or both of them, they're going to have a unique property to them. You'll see what happens here. So this is the working model that we're going to have, this reduced one at the very bottom. Okay, so they reduced it down to this, like I just said, and the denominator is reduced, and now, notice if you look at the domain now, it's only this is your bad number. Now, what's the tricky part is, in the very beginning, we said the domain cannot have 1 and it cannot have negative 1. Okay, that's from the very original, that equation right here. And try it if you're not sure. If you plug in 1 to that equation, the original, it will get a 0 on the bottom, so you can't have it. If you plug in a negative 1, it'll get a 0 on the bottom. You can't have it. So those numbers are out. So what I like to do is I like to indicate that on my graph right now with a couple of dotted lines. Now they may not be asymptotes. You'll see what happens in a second. When we reduce this, notice the 1 is no longer a problem, but the negative 1 is still a problem. If it's still here, that means this is an asymptote. If the vertical, the bad number here, the 1, if it's no longer a problem, this is going to be a hole in the graph. Okay, that's the difference of these. So you first have to check what's in the bottom, and you see if it cancels off, it's no longer an asymptote. So reduce it down, whatever's left, that right there, this negative 1, that's your vertical asymptote. That's it. So to answer the question, what's your vertical asymptote? It's just x equals negative 1. All right, so the horizontal asymptote, the numerator they both have a degree of 2. Okay, so what happens is there's a shortcut here. If they both have a degree of 2, like if they have the same degree. So remember we talked about that formula. If the degrees are bigger on the bottom, if the bottom has a bigger degree than the top, then our horizontal asymptote is going to be y equals 0. Well, that's not the case here. They have the same. So if they have the same, then what's going to happen is, show you a little trick. And they talk about coefficients and all that, but I'll give you a little easy trick. This, again, only works if you have the same degree. So let's say right here, you have the same degree on the top and bottom. What I say is, you take just those high powers, the 2x, the 3x squared and the 2x squared, 3x squared and the 2x squared. You cancel these because they're the same, and what you're left with that is the horizontal asymptote right there. Okay, that's where they get this 3/2 term. So remember, this only works if you have the exact same degree on the top and bottom. If they do, you essentially cancel everything out except for the two coefficients, the numbers in front of them, the 3 and the 2. That's going to be your horizontal asymptote. So that's one of your tricks to finding those. Okay, so like I said the other day, feel free to pause this if you need a little more. Go back. If you want to look at this a little more in depth, I'm just going to keep going on this. So, bounded functions. Functions bounded if the entire graph of the function lies between two horizontal lines. Okay, that's going to happen sometimes. You're going to get this, and you'll see this in a second if you have a bound. So let's get to some rational functions right here. New company manufactures computers, and they have established that a new employee can assemble this many components. So the n is representing the number of components per day after t, which is the number of days on the job training. Okay, so this is the fancy formula they gave us, and they want us to sketch this graph. And we're only going to go from 0 to 100, and you want to include any vertical or horizontal asymptotes. So let's go back over what the rules are. I look at this and I see my domain tells me I cannot have -4. That's from me setting that denominator equal to 0 and finding out whatever points make a 0 on the bottom. We can't have those. So we can't have a -4. That is going to be my vertical asymptote right here. T equals 4. The horizontal, well, remember that trick. Look at the degrees. They both have a degree of 1. So for the horizontal, I take just those highest powers. I'll use a y there. And what I'm left with is y equals 50. That's my horizontal asymptote right there. Same trick. Okay, I'll remind you the other rule. If the bottom power, the bottom degree is higher, then it's always going to be y equals 0. If the top degree is higher, then there's no horizontal asymptote. That's going to be that slanted one. So that's all we have there. Okay, so now we're going to sorry. Okay, so now what does the function approach as t increases? Now when they say as t increases without bound, what they're asking here is saying what happens as t gets really big? As t goes to infinity, t is going to get large. They want to know what's happening to the function. So that was the thing I was telling you earlier. Why don't you plug in a big number? Why don't you plug in a really big number or a super big number like that and just see if you can detect a pattern, okay, what's going on. So they're asking what happens as t increases, plug in some numbers, and you're going to start to see the pattern. I can tell you the pattern right now because we know the horizontal asymptote is 50. These numbers are going to get closer and closer to 50, okay? A little bit, I'll show you what I mean. On the 10, you're going to get 500 over 14. On the 100, you get 5,000 over 104. And on this one, you get 500,000 over 10,004. Okay, so you're going to see each of these, if you plug those into the calculator, they're getting closer and closer to the number 50. So that is the behavior of these. That's what's happening on each of these as you move forward. Okay, so. All right, now we're going to talk about some examples of these. Okay, so the domain of the function is t is greater than 0 excludes the value of t for which the denominator is 0. So there is no vertical asymptote for the stated domain. Okay, going back over here, remember, that was an important part. I kind of brought that up where this is when t cannot be -4, but because they quote here, t is only for values bigger than 4, then actually this is the domain right here. This stands. There are no restrictions, no exemptions. Okay, then the horizontal asymptote. Now we have another trick here that we're going to show you here. This is more of an algebra pre-calc, higher level thing, which is good. You guys can do this. When you look at a function, look at every individual term, okay? And the idea is spot the highest power in both top and bottom. So in this case, the highest thing you see is a power of 1. So what you're going to do is you're going to come along and divide every term by t. Okay, now it's unconventional because normally you're not allowed to divide by a variable. You're not supposed to, okay, because the variable could equal 0. In this case, though, since we're trying to figure out what happens when we go way out to the right to high numbers like to infinity, we can do this, and you see what's going to happen. These are going to cancel, these are going to cancel, and we're going to be left with a 50, a 1, and a 4 over t. Okay, and what's going to happen with that is we want to see what happens as t gets really, really big, like high numbers. So just look, there's only one t left in my problem down here. As t becomes 100, 1,000, a million, a billion, this little fraction is basically becoming nothing. It's becoming minute. So we just get rid of it, and what's left is 50 over 1, and that's how we have that y equals 50. Okay, so you see it approaches 50, same kind of thing. There's two different ways to do this, but either way, we are getting 50 as the approach, the horizontal asymptote, y equals 50. Okay, so last one here, we're going to talk about graph an example, a rational function here. So, or keep going with the same one, I'm sorry. Graph the picture is what we haven't done yet. So you look at our graph here, we know that there is no asymptote that we were talking about vertically because it was outside of the range, but we know it's going to be getting closer and closer to 50. So, and the last part is you might just need to go plug in a few points just to see what's going on. So if you plug in 0, you get 0. And remember, they told us originally, let me go back a couple slides to show, we had this, they only want us to go right here between 0 and 100. Okay, so that's really our true domain. So in this graph, they found what 100 was, which is a number very close to 50, but just under it, and then maybe plot a few more points, maybe 2, 4, 6, 8, maybe plug in 50 or 40 or 30, whatever, just a couple of coordinates to get this picture, and you see this is our graph. If they didn't have that restriction of it going up to 100, stopping at 100, then this graph would just keep going forever, but it would never cross this asymptote of 50. That's the limit that we have. Okay, so at this point, I'm going to stop this video. I'm going to re-record another one doing some homework examples just because I don't want this to be too big. So that'll be it for this one in section 1.4 is what we're on, and I'm going to do a handful of problems next out of section 1.4.